Hello everyone. In this lecture, we will study the inclusion and the exclusion formula. Actually, we can view this as a final description of the previous division principle, addition principle. The first main example, which is very elusive, is the following. How to compute the cardinality of the set A union B. If we draw a picture, then it's easy to see. So suppose this is A, this is B, and the red part is A intersection B. Then it's easy to see the cardinality of A union B is, so for convenience in the following, I will call the cardinality just as absolute value with a slightly Bussell notation. It's the absolute value of A plus absolute value of B minus absolute value A intersection B. You can verify this because so just a slightly artificial proof of it. So for each element, for example, X in A union B, if X is in A but not in B, then on the right hand side you will see it contributes 1 to absolute value of A, 0 to intersection B, 0 to absolute value of B, and 0 to absolute value of A intersection B. And if, similarly, if X is in B but not in A, then X contributes 0 to absolute value of A, 1 to absolute value of B, 0 to A intersection B. And if X is in both, then X contributes 1, 1, 1. Therefore, when you look at this formula, you will see we have 1 plus 1 minus 1 on the right hand side, which is 1 equals the left hand side. So from this formula, you can tell this negative sign is very important, or is crucial. Okay, now I suggest you, if you still have a confusion on this proof, please write down a rigorous proof by yourself. It helps a lot. And now we look at slightly complicated example, how to calculate the cardinality of A union B union C. So if you draw a picture, you have red one, you have green one, you have blue one. seems like complicated because you have intersection here, let's see, A, B, C. Here you have AC intersection C. Here you have A intersection B. Here you B intersection C. And in the middle you have A intersection B intersection C. So how to write down the formula? So whenever you have some complicated stuff, thinking of the induction method, that is, we view, so the idea, view A union B as a whole thing. Therefore, by example 1, we can conclude that absolute value cardinality of A union B union C equals A union B absolute value plus C minus A union B intersection C. Okay, then what is A union B intersection C? So here we use the De Morgan formula. So there will be A intersection C union B intersection C. And then if you plug in, then you can simplify the above formula as following, since this is A intersection C union B intersection C. Apply the result in first example. Again, we have A union B plus C minus here A union C plus B union C minus A union C union B union C, intersection C. And similarly, for the first term, you can also apply the formula in first example. That will be A absolute value of A plus absolute value of B minus absolute value of A intersection B plus C absolute value of C minus absolute value of A intersect C minus absolute value of B intersection C plus absolute value of A intersection B intersection C. And if you rearrange the order, then we have a slightly beautiful formula. So we will see actually it's quite symmetric. For a single set, you always take absolute value and then sum them up. And for intersection of two sets, you take the cardinality and give it a minus sign. And then for the whole intersection of three sets, you have plus sign again. Okay, if you understand these two examples, then we can write down the result in its general form as follows. It's an inclusion exclusion formula. So suppose you have n sets, let's assume they are finite sets. Otherwise, you just have infinity equals infinity, and which is useless in combinatorials in our course. Okay, and then you can guess the cardinality equals summation of cardinality of all sets from 1 to n, and the minus the cardinality of all pairs of two sets and do intersection, minus, and then you plus all triples I1, I2, I3, and the compute the summation of cardinality of AI1 intersection AI2 intersection AI3, and blah blah. The last one is minus 1 to nth power plus minus 1 to nth power A1 intersection A2 intersection all the way to AN, and then take a cardinality. Okay, and the proof will be similar to the one we given for the example 2. So we will prove by induction, and by example 1 and example 1, 2, we know that it holds when n equals 1, 2, 3. 1 is trivial, so we didn't calculate it. And now suppose theorem holds for any m between 1 and m, and then we consider the case n equals m plus 1. And now the left-hand side is union of m plus 1 arbitrary sets, finite sets, and you apply the formula for m ones. So here you view it as A1 union all the way to AM and union AM plus 1. Then you apply the formula once. You have A1 union A2 union all the way to AM plus absolute value of AM plus 1 minus A1 union A2 union all the way to AM intersection AM plus 1. Okay, then here for this one, we know that we can rewrite as A1 intersection AM plus 1 union A2 intersection AM plus 1 union all the way to AM intersection AM plus 1. Okay, now you apply by induction the first term here can be calculated as summation 1 less than I1 less than or equal to m AI1 absolute value minus summation 1 less than or equal to I1 less than I2 strictly less than or equal to m to intersection absolute value and plus triple intersections. And whenever you do this this type of formula, keep in your mind the first few terms and the last few terms. So the last one we have is minus 1 to m's power A1 intersection A2 intersection all the way to AM. Or even though you may not need this information, but it's a good habit to keep a record of the last few terms as well as the first few ones. Okay, and then you have AM plus 1 absolute value. You just keep it, and then let's do the formula for the blue part. So for the blue part, you also have firstly you have a big minus sign in front of it. Here. Therefore, here you have minus sign. And inside, you will have 1 less than or equal to J1 less than or equal to M, a J1 intersection AM plus 1, and then minus 1 less than J1 less than J2 less than or equal to M, a J1 intersection AM plus 1, intersection AJ2 intersection AM plus 1, and then plus 1 less than J1 less than or equal to J1 less than J2 less than or equal less than J3 less than or equal to M, AJ1 intersection AM plus 1, intersection AJ2 intersection AM plus 1, intersection AJ3 intersection AM plus 1, absolute value. And finally, you have minus 1 to M's power summation. So here actually you have the only M triple is A1 to AM. Okay, so here you have this formula. And you have big bracket here. Okay, notice that here actually this is AJ1 intersection AJ2 intersection AM plus 1. This is AJ1 intersection AJ2 intersection AJ3 intersection AM plus 1. And this is actually A1 intersection A2 intersection all the way to AM plus 1. And noted that we can reorganize this summation in the following form. Noted that the first few terms, starting from this one to this one, exhausted all the intersections, no matter how many you have, without AM plus 1. And starting from this one to the end, we exhausted all the intersections of which there exists at least AM plus 1 inside it. So finally, if you compare the sign correctly, you will get the right hand side. Let me slowly. The left hand side is intersection of M plus 1 sets, and then the right hand side is what we expect, summation 1 I1 from 1 to M plus 1, AI1 minus I1 I2 M plus 1 intersection, 2 intersection plus minus 1 to M plus 1's power, the 4 intersection. Okay, so by induction, we are done. So next, let's apply this formula to the following easy example. Suppose, so actually this example give a scheme how to apply the formula in the general situation. So find the number of integers among 1 to 100 that are not divisible by 4, 5, or 6. So solution. The first thing is we need to set up what is the correct set and how to apply the formula. First, the whole set S, of course, is all the numbers 1 to 100, all the integers from 1 to 100. And then A, or A1, is 4, 8, 12, 100. And then B, when you only have a few sets, we would like to use ABC instead of A1, A2, A3, since it's more convenient for us, human being. Okay, then for B, you define it to be 5, 10, 15, all the way to 100, divided by 5. And C is 6, 12, 18, all the way to 86. And then similarly, you can compute what is A intersection B. So that would be 20, 40, 100. And 12, 24, 96, 30, 60, 90. And the 4 intersection is 60. Okay, and the question actually is asked for what is complement, A intersection complement of B intersection complement of C. So that will be actually the complement, if you use the De Morgan law, complement of A union B union C, and that will be S minus A union B union C cardinality. And you apply the formula from example 2. You will have, you can just write down all the sets appear in the formula. And if you calculate carefully, you will find it's 54. Okay, I will not repeat the elementary counting. And from this, we can easily write down a slightly different version of the previous inclusion exclusion principle. That is, if we are interested in the cardinality or the intersection of the complements, then we can just use the cardinality of the whole sets minus cardinality of the union. Or if you plug in the formula, you will have this. I suggest you at least write down this formula once. That's a good exercise to practice how to organize the sigma symbol in your formula. Okay, the last one is the 4 intersection. So you have A1 intersection A2 intersection AM. So later on, if you are familiar with this formula, you can just write down the first few items instead of writing down the last one. Okay, then a similar example. So how many permutations of the letters M, A, T, H, I, S, F-U-N. Math is fun. Are there such that none of the words math, yes, and fun occur as consecutive letters? The solution will be similar to the above one. So the whole set is permutations of MATHISFUN, and let A be the permutations containing MATH consecutively, and let B be permutations contain yes consecutively. C is permutations containing FUN consecutively. Okay, then let's compute what is cardinality of S. Since you have 1, 2, 3, 4, 5, 6, 9 letters, so cardinality of S is 9 factorial. And for A, since math appears consecutively, so you can view this as a whole thing. Therefore, you can view this as permutation of 6 letters. So this is 6 factorial. Similarly, set B can be viewed as permutation of 8 letters, 8 factorial. C is 7 factorial. And similarly, A in section B can be viewed as permutation of 5 letters. So you can just write down the cardinality easily. Okay, then the cardinality or the permutation, the number of permutations asked by the question is by the formula is cardinality of S minus cardinality A minus cardinality B minus cardinality C plus A in section B plus A in section C plus B in section C minus A in section B intersection C. So you can plug in. Okay, and another very similar question is, so how many integers between 0 and 99999 inclusive having among their digits each of 2, 5, 8. Solution. So the most important thing to do in this type of questions is to set up the whole set and the basic ones, the basic A1, A2, A3. So here sets S is of course all integers, and A no digits 2 equals 2 equal 2. B is no 5. C is no 8. And then it's easy to see that the cardinality of S is 10 to 5. Cardinality B is 9 to 5. Cardinality A equals cardinality B equals cardinality C equals 9 to 5. And the two intersection equals 8 to 5. And triple intersection equals 7 to 5. Then the whole number is given by this. Okay, and here you will see that the coefficients here is very similar to the one when we expand x minus 1 to cube. This is not a coincide because we have the following remark. If the cardinality of intersection depends only on the number of sets appear in the intersection, then the formula can be largely simplified and as following. Okay, so those are binomial coefficients. And before we proceed, recall example we studied before. That is, we find the formula for the number of R combinations of the multi-sets. For example, infinite A, infinite B, infinite C. And this problem actually is equivalent to find the number of integer solutions of x plus y plus z equals R, x, y, z, non-negative. And the answer is well known, R plus 2. And here, choose R or choose 2. So they are same in this question. And we made a remark before that the formula star holds when the bounds here, when the upper bound for x, y, z larger than R. Okay, and then the question is, what if the bound appears less than R? So for example, what is a number of 10 combinations of the multi-sets 3A, 4B, 5C? So the solution is we view this as, or we embed this into a larger set and view this as application or inclusion exclusion formula. So we know that when you have a bigger multi-set, infinite A, infinite B, infinite C, this which is better understood. and then let S be 10 combinations of T tilde, and A 10 combinations of T tilde with more than 4 A's, and B 10 combination of T tilde with more than 5 B's. C is more than 6 C's. So where 4, 5, 6 come from? This is because here original T only have 3 A's. So if you have more than 4 A's, then this cannot be counted as solution to the original question. Similarly, when you have more than 4 B's in your combination, then it's not a solution to the original question. And similarly here. Okay, then if you apply that, you will see that actually the question can be transformed into the following one. What is A complement in section B complement in section C complement? Okay, then we can apply the formula before. And to use the formula, we need to calculate all the ingredients inside the formula. For example, the cardinality of S by the original formula star, we know is 12 choose 2, which is 66. And the cardinality of A, recall that the question has an equivalent formulation as an equation. Okay, then if you let x prime to be x minus 4, okay, then you will have an equivalent equation, while the equivalent equation is in the original form. Also here 6. This is crucial. And then apply it, you will have this is 8 choose 2, which is 28. And similarly, for B, you have 7 choose 2. And for C, you have 6 choose 2. Okay, and then for A in section B, the original question is formulated in the following equation, system of equations, and then it's equivalent to, let's say, x prime equals x minus 4, y prime equals y minus 5. So this is x prime plus y prime plus z equals 1, x prime greater than 0, y prime greater than 0, z prime greater equal to 0. Okay, so this is 3 choose 2, and then similarly A in section C is 2 choose 2, B in section C is 0, and A in section B in section C is 0. Therefore, totally you have 66 minus 28 minus 21 minus 15 plus 3 plus 1, which is 6. Okay, so the main point of this example just give you an idea how to apply the formula to the original combination, K combination problems. And actually for this one, you have an easy way. Actually, you can enumerate. Because totally you have 3 plus 4 plus 5, 12 elements. So the question is equivalent to dropping to drop 2 letters. Okay, therefore you can drop A, B, AC, BC, BB, CC. So totally you have 6 ways. Okay, now let's look at a similar question. So what is a number of integral solutions of x1 plus x2 plus x3 plus x4 and satisfy all these inequalities. So the idea first, we need to transform into a slightly standard form. That is, we set y1 to be x1 minus 1, y2 to be x2 minus -2, y3 equals x3, y4 equals x4 minus 3. Then you have the summation is -1 plus 2 minus 3 is 16. And the y1 less than 4, y2 less than 6, y3 less than 5, y4 less than 6. And let's set let S to be set of all the integral solutions of summation yi equals 16, yi greater than 0 for I 1, 2, 3, I equals 1, 2, 3, 4. So this kind of like the free problem, the K combination of infinite multisets. And then let A1, when you have more than 4 subsets appear in your basic formula, then it's better to use A1, A2, A3, A4. Because A, B, C, D kind of more complicated. Okay, then A1 will be set of all integral solutions of summation equals 16 and y1 from 1 to, y1 greater than or equal to 5, and the remaining stay the same. And the A2 will be integral solutions of summation equals 16, y2 greater than or equal to 5, y1, y3, y4 greater equal to 0, and the A3 is integral solutions of summation yi equals 16, y3 greater than or equal to 6, y1, y2, y4 greater than or equal to 0, and A4 is integral solutions of summation yi is 16, y4 greater than or equal to 7, y1, y2, y3 greater than or equal to 0. Okay, and as we mentioned before, so here this 5 corresponds to 4 here. This 7 corresponds to 6 here. Similarly, this 7 corresponds to 6 here. This 6 corresponds to 5 here. Okay, next we can compute the cardinality by the original formula. So the cardinality S is 19 choose 3. Cardinality A1 is you can compute use the calculator, but I will just write down the answer directly. So A1 is 16 minus 5 plus 3, choose 3, which is 3, 6, 4. A2 is 16 minus 7 plus 3, choose 3, 220. A3 is 16 minus 6 plus 3, choose 3, 2A6. A4 is 16 minus 7 plus 3, choose 3 is 220. A1 plus A2. A1 in section A2 is 16 minus 5 minus 7 plus 3, choose 3, 35. A1 in section A3 is 16 minus 5 minus 6 plus 3, 56. A1 in section A4. The computation is heavy, to be honest, but the idea is simple. So as soon as the idea is clear, you can use the computer to calculate it, or even if you do it by yourself, you won't miss something. So the key problem, I believe you already get the idea when you do the exercises. The key mistake you will probably make is that you will miss something or annually add some wrong thing. So when you apply this formula, everything is clear. You just work with the sets. So nothing to confuse with, just a calculation. Okay, 16. The model is clear. Okay, and when you have triple intersection or quadruple intersections, you have 0, and then you just sum them up. So I will write down the answer. Is 55. Okay, and another question actually is how to enumerate in the way dropping letters. Actually, you need to drop 5 letters, and there are not so many possibilities. So you can compute in that way. Probably it's simpler. Okay, I will stop here.